Mercury. The name evokes images of speed, cunning, and mystery, a fitting title for the solar system's smallest and closest planet to the Sun. But Mercury is far more than a scorching ball of rock and metal. It is a world of extremes, a planet of paradoxes, and a custodian of secrets buried deep beneath its sun-scorched surface. Unlike its neighboring terrestrial planets, Earth, Venus, and Mars, Mercury bears the scars of a violent, turbulent past. Its cratered surface, etched by countless impacts over billions of years, tells a story of cosmic collisions and celestial upheaval. Yet, beneath this battered exterior lies a dynamic heart, an interior still cooling, still evolving, still holding onto a lingering heat from its fiery birth. For centuries, Mercury was dismissed as a barren wasteland, a lifeless rock baked dry by the unrelenting proximity of the Sun. But recent decades have revealed tantalizing hints that Mercury might not be so lifeless after all. New data from spacecraft orbiting the planet has shattered assumptions, revealing that Mercury's interior is far more complex and active than previously imagined. And with this complexity comes a profound question. Could Mercury, despite its hostile surface, harbor conditions suitable for life? Could it be that beneath its frozen polar shadows and sun-baked plains, in its slowly cooling core and hidden reservoirs, life has found a way to persist? This is the story of Mercury's cooling secret, an epic tale that bridges planetary science, astrobiology, and human curiosity. A tale that challenges what we know about habitability and forces us to rethink the possibilities of life in our own cosmic backyard. Join us as we journey to the smallest planet, to the very edge of our solar system's furnace, to explore the hidden heat within Mercury's heart, the frozen whispers of water ice in its shadowed craters, and the subtle chemical signatures that may one day reveal the presence of life itself. Mercury's origins lie shrouded in the dawn of the solar system, a time of chaos, creation, and cosmic violence. Over 4 billion years ago, a vast disk of gas and dust swirled around the newborn sun, condensing into planets through collisions, accretion, and differentiation. Among these infant worlds, Mercury formed quickly, its destiny forever shaped by both its size and its proximity to the solar furnace. What sets Mercury apart from its terrestrial siblings is its extraordinarily large iron core, an anomaly that has puzzled scientists for decades. While Earth's core makes up about half its radius, Mercury's core accounts for nearly 85% of its entire size. This dense metallic heart weighs heavily on the planet's evolution, dictating not only its gravity, but also its internal dynamics. How did Mercury's core become so large? Some theories suggest violent early collisions stripped away much of its original rocky mantle, leaving behind a dense, iron-rich core. Others posit that solar winds and extreme heat vaporized lighter materials, reshaping the planet from within. But the real intrigue lies beneath the surface. Mercury's core is not a dead relic frozen in time. It is a furnace that still pulses with residual heat. This heat drives slow, powerful convective currents, a planetary dynamo that generates Mercury's surprisingly strong magnetic field, the only one among the innermost rocky planets. As Mercury cools, its core contracts. This contraction is etched on the surface in the form of massive scarps, towering cliffs hundreds of kilometers long, rising several kilometers high. These planetary wrinkles are a cosmic record of Mercury's shrinking interior, a process ongoing even today. Yet cooling does not mean dead. Within the heart of Mercury, heat drives chemical and physical processes that may create niches of chemical energy, pockets where life's building blocks could form and persist. Could this slow cooling be the engine behind a hidden biosphere, a sanctuary for life beneath an otherwise hostile world? In stark contrast to Mercury's blazing dayside lies a world of eternal night, the polar craters where sunlight never reaches. In these cold traps, temperatures plunge below -250 degrees Fahrenheit, cold enough to preserve water ice in an environment seemingly impossible for liquid water to exist. The discovery of ice on Mercury stunned the scientific community. How could a planet so close to the Sun harbor such a fragile substance? Radar observations first revealed bright patches near the poles, later confirmed by orbiting spacecraft detecting hydrogen signatures consistent with water ice. This ice is not simply a leftover from cometary impacts. It hints at a dynamic volatile cycle. Trapped beneath layers of dark, organic-rich material, these icy reservoirs may be shielded from sublimation, preserved for billions of years. But even more intriguing is the possibility of subsurface volatiles, water and other compounds trapped beneath Mercury's crust, warmed just enough by the planet's cooling interior to remain stable. Recent data from NASA's Messenger mission showed signs of unexpected chemical compounds and volatile elements in Mercury's surface and exosphere, challenging prior assumptions about its composition. These volatiles suggest that Mercury is not as dry or inert as once thought. Moreover, the interface between Mercury's cooling core and volatile-rich layers might create the right chemical gradients and energy sources necessary for life. Environments where water and heat combine with minerals to fuel prebiotic chemistry or even microbial life. The question then becomes, is Mercury a planet of ice and fire, where the cold of space and the warmth of the core collide, crafting oases of habitability beneath a harsh exterior? Life is a master of survival, emerging and thriving in places once considered uninhabitable. On Earth, extremophiles inhabit boiling hot springs, radioactive waste, and the crushing depths of the ocean floor. If life can endure such extremes, could it exist beneath Mercury's surface, in protected niches warmed by internal heat? To explore this possibility, scientists combine data from planetary missions with laboratory experiments simulating Mercury's interior conditions. Messenger's instruments mapped Mercury's magnetic field, surface chemistry, and polar ice, laying the groundwork for the upcoming European-Japanese Bepi-Colombo mission, which promises to deliver even more detailed observations. Future missions may carry sophisticated instruments designed to probe below the surface, radar to map underground structures, spectrometers to detect organic molecules, and seismometers to study Mercury's internal activity. In the lab, researchers recreate the intense radiation, temperature swings, and chemical environments of Mercury, testing how organic molecules might form, survive, or even replicate under such conditions. These studies are vital for understanding the limits of habitability beyond Earth. The search for life on Mercury transcends simple detection. It is a quest to expand our definition of life's possible habitats, to challenge the Goldilocks zone concept, and to open our minds to the possibility that life might exist in worlds once dismissed as barren and lifeless. Mercury's cooling secret beckons us to reconsider the very nature of habitability and life in the cosmos. This tiny, sun-baked world, long overshadowed by its larger neighbors, now emerges as a candidate for hidden activity and perhaps even life. The journey to understand Mercury is a testament to human curiosity, technological ingenuity, and the spirit of exploration. It reminds us that even in the most unlikely places, the universe might nurture life's spark. As we prepare for new missions and develop better tools, Mercury stands as a symbol of cosmic resilience, a world where fire and ice coexist, where extremes create opportunities, and where life might quietly persist beneath the surface. In the grand cosmic story, Mercury challenges us to look beyond appearances, to seek life in unexpected places, and to embrace the unknown with wonder.